Hello everyone, I'm thrilled to have you join the online course Easy Geosteering. We make complex geosteering topics simple by breaking them down into easy-to-grasp concepts. We're currently in the first part of the course, Necessary Theory, and in the previous video we covered structure map and offset well. And today we will define the term geosteering and list 7 modern geosteering tools available today. Let's get started. So, what is geosteering? It's changing of well trajectory while drilling in order to complete all geological tasks. Of course, the first and most important task is drilling site target layer, but it's not the only one. We will list 3 more points and see how they might appear using one drill example. So, to evaluate the first task, we introduce a term drilling efficiency. It's a relation of productive length to total length of the well. This parameter is set by the customer based on the quality and consistency of the target layer in the drilling area. In this current example, this parameter is 90%. It means we need to drill at least 900 meters inside target to meet the objective. The success of the first goal, among other things, depends on how accurately we enter the target layer. That's why the second task defines the required inclination at T1 point. In our example, it needs to be between 85 and 87 degrees. The third task describes the position of the casing point in the landing section. Here we have just 2 options. The casing point can be either above the top target or below it, depending on the specific project. In other words, this task requires us to stop drilling the landing section at the right point with the right inclination. In our example, the casing point lies below the top target. We need to enter the reservoir and stop drilling 20 meters inside it with inclination of 87 degrees plus or minus 1. So, the set of tasks and their weights completely depends on the specific project. Most often you will see the 3 we mentioned, but you might also come across some additional ones, for example, to get more geological data. If the drilling area is not well explored and there are very few offset wells, in horizontal section you might be asked to cross the top or bottom of the target to clarify its position along the current well. This data will then be used to update the structure maps for upcoming wells. In our example, we need to cross the top target with the gamma ray sensor, but we cannot lose more than 50 meters MD of the reservoir. Okay, we considered the basic geological goals, and if we combine them, we can say that the global geosteering task is the optimal wellbore position relative to the reservoir. To solve the global task, we need to break it down into local ones, and the local goal is to determine wellbore position at every moment while drilling. How can we reach that? By using special geosteering tools. As we mentioned earlier, there are 7 different tools available today, and in this course we will cover all of these methods in detail. But for now, let's do a quick review to get a general understanding. The first and one of the earliest geosteering tools is the model method. The main idea is to determine the wellbore position by comparing current real time and offset well logs. For this, on the horizontal track we have a modeled curve. The offset curve projected onto the wellbore trajectory along the geosteering horizons. This curve depends on the geosteering model and can change its shape. So we adjust segment deep to get the best correlation with the real-time curve, and when that's achieved, it means our model is close to reality. So the model method is the software solution, and as a result of this method, we get the deep angle for each segment and in this way determine the wellbore position on the section. The second point is well correlation. It's not originally a geosteering tool, many services use it, but for us it's also very helpful, especially in the landing section, where we need to predict the TVDSS of the T1 point. In this example we have an offset and a current well. To predict the TVDSS of the T1 point, we assume that the formation between marker 1 and marker 2 has the same thickness in both wells. This gives us a certain TVDSS value and helps to decide whether to adjust the plan T1 point or not. Well correlation is a software solution, and besides TVDSS prediction, it also allows us to estimate the level of lateral changes between nearby wells. Third point is the stratigraphic method. It's a relatively new software-based solution and a powerful geosteering tool, since it offers a great balance between technical possibilities and cost. It's also about geometry and trigonometry like model method, but from some different point of view. The heart of this method is the special scale true vertical thickness, or TVT. Using this scale on the vertical track gives us fundamentally different results compared to the model method, and we'll discuss it in great detail in part number 3 of the course. As a result of this method, we get the deep angle for each segment and determine the wellbore position. And as we mentioned, it's a software-based solution, but not every geosteering software includes the stratigraphic method. That's why we conditionally refer to it as Type 2. Point number 4, borehole images. It's azimuthal measurements with low depths of investigation, which shows us how we drill relative to the formation, stratigraphically up or down. Upward direction means we move from bottom to top, downward means from top to bottom. Don't confuse it with vertical direction, because stratigraphic direction depends not just on inclination, but also on the formation dip. So, borehole images look literally like a whole picture, since it's not a single curve, but an array of data. For example, a density image consists of 16 sectors or 16 density curves. How to interpret this picture? By the shape of the conditional smiles. A smile face indicates we are crossing the bed boundary in a stratigraphically upward direction from bottom to top. A sad face means we drill stratigraphically down from top to bottom. This type of logging is an extremely useful addition to the previous methods, since it can help in complex geological conditions where neither the model nor the stratigraphic method can. To get borehole images, we need to have a neutron density downhole tool. Since these measurements have a low depth of investigation, about few centimeters, such tools often have a special stabilizer to reduce the distance between the sensors and the formation for more accurate readings. Point number 5, well placement. It's also about a separate downhole tool in the BHA. This tool has special tilted receivers which provide us with deep directional resistivity curves with a high depth of investigation, about a few meters. These curves allow us to detect the distance to the non-reservoir and also determine whether it's approaching from above or below. Based on this data, we can build an inversion picture and adjust the well trajectory in advance without leaving the target layer. Well placement is a powerful geosteering method, but it has some geological requirements to work properly. It's also not always economically justified, since this service is the most expensive in the industry. But if we have it, we get proactive geosteering and can detect several surrounding layers while drilling, which can significantly help us perform geological tasks. In addition to downhole tool, this method also requires special software for inversion calculations, which we conditionally refer to as Type 3. Nowadays, apart from tool manufacturer service companies, such calculations can be performed only in StarSteer software by Geology. Point number 6. Two-layer inversion of non-azimuthal resistivity. The point is that if we're approaching a contrast boundary using a standard resistivity tool, its conventional curves will start to separate as well. We can run an inversion process and get a picture of the boundary, just not as far as with a well placement tool, because the depth of investigation here is about 1.5 meters. This method also has stricter requirements to work properly and can detect only one boundary within volume of investigation. But the key point is that this is just a software solution and we don't need an expensive downhole tool. we simply squeeze the maximum out of standard resistivity data. And in some projects with clean and homogeneous formations, it can be really useful. And the last one is auto-geosteering. We let artificial intelligence work for us and find the best correlation between current and offset well logs. As a result, we get a ready-to-use geosteering model, but it still needs to be double-checked since we work in high uncertainty conditions, and AI cannot fully replace a real engineer, at least for now. In other words, auto-geosteering is like our assistant. We treat it as a second opinion. As we upload new MLWD data into the project, AI updates the model in real time. This module isn't available in every software package, so we conditionally refer to it as type number 5. Okay, we have briefly covered 7 modern tools available now in the industry. Now let's move on to the main requirements for a routine geosteering job. So, when you're working in shifts and supporting the drilling process, you need to follow 3 simple rules. First of all, your recommendations about trajectory changes must be in a timely manner. It doesn't mean that you need to react on every single gamma ray reading, for example, but when you have enough reasons for trajectory changes, you have to do it immediately. You should strike a delicate balance between too early and too late reactions. You need to be in right time. Second point, your recommendation should be justified. When the picture is clear, everything is simple. But what to do when we have 2 or more alternative wellbore positions? The answer is you need to analyze all available data and choose the most likely model in your opinion. In other words, you should be able to explain and justify your recommendation. And finally, when you have formed your recommendation, it's necessary to coordinate it with the client because the final decision rests with them. So be in time, justify your recommendation, and coordinate it with the client. Alright, we gave the definition of geosteering, outlined main geological tasks and geosteering tools. Hope you liked this video. Remember, you can elevate your geosteering skills with the private lessons. We work in StarSteer utilizing all modern geosteering tools and drilling simulators to immerse you in the experience of real geosteering engineer. So stay tuned and give this video a thumbs up. In the next lesson, we will explore what makes our work more difficult, key uncertainties and lateral changes. See you then. Bye-bye.